Okay, so you are looking at cyclic codes, and I think I'm going to summarize this soon, and then we are going to start actual codec for DNA storage, how to build those things. Initially, I will explain to you how the very first primitive way of doing it, and later on, of course, now there are more sophisticated ways of doing it. So I'll start with that, the paper in 2012, and then in 2013, and then our paper also from 2013. So I'm going to explain to you how actually codec was designed there. Anyway, so the cyclic code, I think you remember, it's a linear subspace, a vector space, and also if you take a vector, its cyclic shift is also there, right? We saw that basically, if we take the whole space like C23, we can map it to a bunch of polynomials, and so this is also a cyclic code, of course. But if you look at a subspace, okay, so cyclic code corresponds to basically ideal in this polynomial ring, which is Z2X. Okay, so ideal, for example, here it is given by 0, 1 plus x, 1 plus x square, and x plus x square. If you recall, this is an ideal. Okay, so ideal means, so basically, if you take two polynomials, you add them, you are again in the set. And if you take one scalar from the ring, so Z2X, you take any polynomial from Z2X, multiply with element here, you will stay here itself, right? It's not, it will not go outside the set. Okay, so these are the two essential basic things. So basically, this is an ideal. So now, each ideal has a generator polynomial, means a polynomial which can generate all members of the set. So for example, if I take 1 plus x, right, and if I multiply 1 plus x from the elements from ring, we can get all these four. You can see that. Okay, so like that. So normally it's a least degree polynomial in the whole space. So each ideal has this kind of generator polynomial. Okay, so that is something really interesting to see. Now that means so basically an ideal is principal ideally formally an ideal is principal ideally if there exists an element A in I such that I is generated by not A, actually should be G, right? Anyway, that's if there exists G in I such that I is generated by G, that means this is nothing but R times G such that R belongs to R. R is our Z2X here, right? All polynomials, 8 polynomials. If you take an element from Z2X, multiply with this G, like 1 plus X here, you will get all the 4 members. Ideal, this ideal is generated by 1 plus X because R times 1 plus X is I. For every R in those members of Z2X, right? All those 8 polynomials. Okay. So Z2X have this condition that whenever there is X cube, that will be 1. You need to keep that thing in mind, right? So formally, without giving any proof and everything, but I can just tell you, if C is a non-zero cyclic code in the ring Rn, Rn is Z2X modulo x power n minus 1. Okay. There exists a unique monic polynomial Gx of a smallest degree in C such that C is generated by Gx. Generator polynomial. Okay. You saw that. And Gx is, and this is important thing because this gives us a mechanism to find the cyclic codes. Gx is a factor of this polynomial x power n minus 1. This is a beautiful fact. So basically, because that condition we put, right, here x cube is equal to 1, that gives you x cube minus 1. So if I have to find Gx, I just factorize x cube minus 1, whatever factors are there, that can act as a generator of a cyclic code. That's a beautiful way you can actually construct the cyclic code. I'm, of course, these things can be proved, but I'm skipping all the proofs right now. But and once we have Gx, I can get the generator matrix from it. Gx is something like 0 plus Z0 plus Z1x plus GR x is for R. So generator polynomial, so generator matrix is you take the coefficient, put all the zeros, and then just shift. Okay, and you get the generator matrix from the generator polynomial. Okay, so there is a correspondence here. Now you see, the question is how to find all binary cyclic codes, say of length 3. So what I can do, yes. Yeah, so because the degree up to R, right? Total length is N. You put all other zeros, then keep on circulating. No. One row should be a full zero, you are saying. No, if it is a zero vector, then it will not form a basis anyway, right? Generator matrix is bunch of vectors in the basis space, basically, right? Which can give you all the code words, right? All basic linear algebra, right? Anyway. So now, in order to find, like, suppose I say that find all cyclic codes of length 3, I just look at the polynomial x cube minus 1 and factor it. You see that this is the factorization. You multiply this, modulo 2, you will check that you will get x cube minus 1. Everything is modulo 2 here, right? So, and so x cube plus x square plus x plus x square, 2x square will be 0. And then x, that will also go to 0, right? You are left with x cube plus 1. Minus 1 is same thing as plus 1, right? X cube plus 1 or x cube minus 1, because we are working over modulo 2, right? So this is, so only thing is to factorize. So now how many cyclic codes are there of length 3? I can find it out. How many factors are there? One factor is 1. You can take that also, that's a trivial case. Right? Another thing could be take product of both, that's also a trivial case, and 2 more. Right, so one is, if you take generator polynomial as 1, you will get all of the ring R3, all 8 polynomials you will get. Essentially, you will get all of the whole space corresponding, if you look at the vector space, right? If you take generator polynomial as x plus 1, you saw this is an example of the generator ideal, okay? And the cyclic code and the corresponding binary vectors you can map. Polynomials you can map to binary vectors you can map to polynomials, right? So you get this factorization, right? I mean this space. If you take the second polynomial x cube square plus x plus 1, you get only this ideal having only 2 elements, 0 and 1 plus x square, which is your friend. 0, 0, 0, 1, 1, 1, you remember? Repetition code, the first one. You see, such a beautiful thing. Just look at a polynomial of some degree, factorize it, and you get bunch of codes, whatever you want, right? It's a powerful mechanism, right? And when you take product of both, you get x cube minus 1, which is 0 actually, because x cube is equal to 1. So you get 0 vector. I mean 0 polynomial, it's 0 vector. Okay. So just by factorizing x cube minus 1, I got all, how many cyclic codes are there? 4. Right? So if you know the efficient algorithm of factorizing x raised to n minus 1, you can generate as many cyclic codes as possible, right? And luckily, your beautiful code, because 0, 0, 0, 1, 1, 1 is a beautiful code. Why? Because you saw when we draw the spheres of radius 1, it was perfect code, right? They cover the whole space. That is also cyclic code, you see? Right? So this is the overall picture. If I want to construct a cyclic code, just look of some length. Say, suppose I want to construct a cyclic code of length 7. Just look at x raised to 7 minus 1, factorize it. Okay, modulo 2. And then look at each individual and you can get a code. Okay, this is a very nice technique for construction of cyclic codes. And here is a factorization given to you for table up to length 10. I've already given. So length 1, 1 plus x, you know, x plus x minus 1 is same thing as x plus 1. That's first. And how many cyclic codes are there? 1 and x plus 1. 2 will give you. Second, x square minus 1. X square minus 1 is same thing as x square plus 1, which is nothing but x plus 1 whole square, modulo 2. Because x square plus 1 plus 2x will be 0. So x square plus 1, right? So essentially you get how many? 3 codes. 1 plus x, and 1 plus x square. Right? 3 possibilities. So you get 3 cyclic codes. Degree 3, you saw there are 4. I just showed you whole table, right? So as an exercise, I would say that up to length 10, just work out corresponding cyclic codes, right? So one trick that you need to know how to factorize, right? Which is a nice mathematical problem. How do you factorize of degree in polynomial? There are techniques and so on and so forth. Okay. So you see, degree 7 is important. N is equal to 7 gives you 8 codes. By the way, you know the length 7 code is which one, which I told you, the popular code? 743. I told you about a code, Hamming code. You get from factorization. Such a beautiful mechanism, right? That code is also cyclic. So Hamming code, the way I told you, take those polynomial, those columns which are not multiples of each other and so on and so forth. That is one construction. Another one is just take the polynomial x raised to 7 minus 1, factorize it, and one of them is sitting here. Okay, so you can construct the Hamming code also from there. So all these things are coming from this. So essentially, that's why we say that cyclic codes are something very, very important, because this class contains many good codes actually. Okay, and so you will see that idea, because Hamming code is a cyclic code anyway, the many case, you can generalize that, and finally you will get VCH code, Bose-Chaudhary-Hockingham code, which is very good from engineering point of view, and they are also cyclic code. So basically, all you need is a generator polynomial for the construction of the code. Once you find a generator polynomial, you get the generator matrix and everything is there, right? Since polynomial business is easy to implement, encoding, decoding, and everything, it's a very efficient. Algorithms are available for doing many things. Okay, so that's why most of the codes which we use are cyclic, because easy to handle all the machinery, right? So that's why cyclic codes are very, very important. So which one?
We get this like when we use generator 1, so we should get 0, 1, x and x square, right? It should be like in case of this, we wrote all of that. Shouldn't this be generated?
No, but then this should give you the whole space, right? Because you see, this will give you all 8 factors. Basis has 3 elements. This is 0, 0, 1, 0, 1, 0, 1, 1, 0. These are 3 vectors are linearly independent. So how many vectors it will generate? 8 vectors. This is the case of the whole space. All vectors. All vectors. Got it? So basically here, when you multiply the first one, I think the first case or the last case, I can show you. Yeah, the first case, 1. When generator polynomial is 1, that's what you are getting, because 1, x square, right? All of our thing, whole thing. This is cyclic code, yes. This is the no, it's all, because see what happens if you take only these 4, then it is not a linear space. Because if you sum them, it will be out of the things, right? 1, 0, 0 and 0, 1, 0 is 1, 1, 0, which is not there in the set. Right? Got it? So what I was saying, that finding these factorization is a task which is a difficult one, of course, but beautiful one. I mean, you can see how do we find these things. Okay. So I think as an exercise, I would suggest you look at Reed-Solomon code. What is the generator polynomial? GX for Reed, which is a very popular code, standard. For most of the storage, Reed-Solomon code is used. Reed-Muller code, Hamming code, what is GH, and BCH code, what is generator polynomial for these cases. Okay, I you just explore what are the generator polynomial. That's all. Okay, you don't have to go into too much stuff. Okay, so that was all about the summary of basically basic codecs, some idea. So up to the cyclic code, I covered most of the stuff. So essentially, code is nothing but a subspace, so vector subspace, right, of a vector space. It has parameters n, k, d. D is the Hamming distance, k is the dimension, and n is the length, right? If I have to find a good code, essentially I am saying that we should look at cyclic code, and the cyclic code finding is very easy. Just look at the polynomial x power n minus 1, factorize it, and then you are done. So now comes the year 2012. Of course, before that, people have tried to convert some media things into basically some plain text into DNA by simple encoding, right? Simply binary encoding, like A could be 0, C could be, A could be 0, 0, C could be 0, 1, G could be 1, 0, and T could be 1, 1, something like that. It's very simple. And without thinking about any error correction thing and so on and so forth, just convert it and they try to do the experiments before 2012. In 2012, actually, because if you want to look for large media file, if you just one sentence is okay, but if you want to go for large media files like doc file, PDF file, PowerPoint, and so on and so forth, so you have long byte string, right? And as I mentioned, the sequence in synthesis, normally we get DNA strings of length 300 maximum, depending upon which machine you are using, or even less than 300. That size is up to 300. So we need a mechanism to convert byte string into ACGT such that errors could be minimized. And the most common error that was observed during that time was sort of deletion. Deletion. Still today also it is very common. Deletion error. So once a bunch of bits will be deleted. So when ACGT, when you are reading or writing actual DNA in this part, sequencing means reading, or synthesis when you are writing the DNA, physical DNA, these errors will happen quite often. So now what to do? We need a mechanism of converting byte strings to ACGT such that basically AA, CC, GG, TT is not repeated. Okay. So like in the DNA strand, we should not have AA, CCC, GG, like that, right? This should not be there. If there is A, next symbol should be different than A. If there is G, next symbol should be different than G, like that. So we need some sort of property. So this is known as homopolymer property, right? So non-homopolymer property. How do we get this? Homopolymer means they are repeating. Non-homopolymer means we should not have this repetition of ACGT. Okay. How do we convert our actual data into these kind of DNA strings? Okay. So let me show you first the initial attempt that was done. Okay. And then how they arrive at the solution. So data source is there. So what we require. So basically, as I mentioned, the size of DNA writing is around 300. So basically, we require chunks. Whole file has to be divided into chunks. Okay. So first you do the data encoding. Means whatever doc file is there, that is very easy. Like just write any byte string conversion will do the job, right? So anyway, the data is in the byte string form, right? All the doc file. So that is in. So here we are getting byte string as the output. Then we convert into DNA strand using a map which is going to avoid repetitions of ACGT, right? And then we divide into chunks because we know that if we try to synthesize the whole big file, it is difficult. The machine has to terminate at certain point, right? So normally 300 is a rough size, even less than that in some machines, right? 300 nucleotides they can synthesize at a time, right? So we need to make these kind of chunks. But actually, even the data will be even more less than 300 because what happens, there is some indexing is required. So what happens if you take the file, convert into these DNA strands, how will you order them? Which, right? Some indexing is required and clever reconstruction techniques is required. Okay, this packet, then this packet, then this packet, and that will combine to give you the whole data, right? Those kind of problems are also there. Then, of course, you store. Basically, once DNA chunks are created, like this is a general outline I'm giving you, and depending upon the which machine you are using, this will vary a little bit. Then the DNA synthesis means you synthesize the DNA using a machine, DNA synthesizer. So normally there are 3 techniques of DNA synthesizer that machines are using. The modern one is enzyme based, but anyway, and then so data is stored, right? And whenever you want it, sequencing is reading the data. No, sequencing is normally the term used for reading the data. It's a common term because of biotechnology industry. They were not using it for reading or writing as such. Okay. They wanted to read the genome data, right? So they call it sequencing. Okay. So indexing will decide actually. There is a way. I'll show you some basic things. Okay, initially. Okay, so then DNA is stored, synthesis is done. Then when you read them, in sequencing them, and sequencing technology has been advanced quite a lot. There are nanopore sequencing which can read data bit by bit. Okay, so it's very fast. Next generation sequencing is there. Once you decode the data, basically from DNA, then data decoding has to be done. Means reconstruction algorithms will work here and so on and so forth, and they will give you the actual data. And then, of course, some errors might happen during any of these process. You need to recover so you need to do the error correction. Okay. In the initial papers, the first paper it was done in 2012, it was done manually first. In the second one, they used 4-fold redundancy to correct the errors. And finally, data is retrieved. Okay. So this is a very, very basic outline. Take the byte string, okay, convert into the DNA string, divide into chunks, write down chunks, and then actually, of course, there has to be chunk architecture. Just like that, you remember in our internet, there is a data packet, there is a header, this and that. Those kind of things will be there also. Okay, some indexing, some header, and something, And so once data is synthesized, then you can actually read it using sequencing mechanism, decode it, and then correct the errors. Okay, and then once you correct the errors, get the data. Now, basically, there are 3 common types of errors that happen: substitution, deletion, and insertion. Okay. This is something very, very common. As I mentioned, deletion happens quite a lot. That depends on which will happen and so on. So people who are willing to develop the simulator, they have to introduce these kind of errors randomly into the system, right? And then you should be able to reconstruct, right? Those kind of things you have to do. So we are going to give you one file, you take the file, do all this process through software, then simulate it, the error, right? And then recover and see how much you can recover. That's what's the job of simulator, right? And since many people are interested in developing simulator, it will be a very nice thing. Already there are 3-4 simulators available. There is one company which has developed one. Microsoft has one simulator. Yacobi Group in Israel, they have one simulator actually. So everybody is developing a simulator, right? So a simulator is good enough to see what is going on, right? Okay. So they try to create the scenarios, especially people from computational science background. This is very natural thing to develop simulator, right? Okay. And so this requires a different kind of coding theory as well, not the codecs, whatever I told you about the Hamming distance for correcting errors. Here they require edit distance, I told you about. minimum number of insertion, deletion, and substitution required to change one string to the other string, right? Because there the length may also change. X vector has some length and the receive vector has some other length, because it may be deleted, right? Or something is inserted, right? Those kind of things are possible. Substitution is simply the Hamming distance kind of case if these two things are not there, right? So as I mentioned, there were so many papers before, especially CAC was the one in 99. But it was very, isolation, one paper in 2003 and then 7 and so on and so forth. So actual thing started in this blue. Church et al., right? George Church in 2012. This is the main paper, which you should read, by the way. And then immediately in 2013, there was a Goldman paper. And we have also done the work at the same time, though we publish it in. So we have this software DNA cloud, which was developed here itself. And then we published our technique, which was there in 2015. I'll show you that actually. Okay. And then there were Robert Grass. He has done a lot of fundamental work there. Olga in UIUC, they have done a lot of work. And then there are so many others who have contributed in that area after that. So this is the tipping point, from 2012 onwards. So some of the references are there, which I would suggest you can look at it. So these blue ones are our work in the initially what we have done. That is the first paper by George Church, and the second paper by Goldman. That you need to read anyway, right? And there are many others, who has done different kind of. So actually, the DNA storage channel you can describe in different manner, holistically and so on and so forth, and study and develop the codecs which are efficient. Still, there are many interesting algorithmic problems that need to be handled. Okay, so there are many things which people are working right now. So let me give you some brief idea. So data source, encoding, DNA coding, these are the major blocks. If I take, because I want to correct code, I want to design a codec which is consisting of DNA strings. On all our previous codec, we were looking at binary strings, 0, 1, right? But now we have ACGT strings of ACGT. So we need to design codecs for that directly. So people have defined what is known as DNA code. Okay, what is DNA code? So if we take sigma DNA to be ACGT, that means cytosine, guanine, thymine. This much information is enough at the moment. I will talk about it more later on. And cDNA is, so basically, initially what happened, people did not worry much about edit distance, but at least Hamming distance is also sufficient. It's an approximate. So you see how many errors we can correct up to that level. So if our error model has only substitution error, then we can actually handle it easily. So cDNA is a subset of sigma DNA raised to power n. So cDNA is a DNA code, length is n, capital M is total number of code words, and D is a minimum Hamming distance. So first, when we saw this work by Goldman, we realized that they have now used efficient code, and we did that. I'll show you how. So main objective is construct optimal DNA codes with maximum minimum distance D to correct more errors. At least substitution errors you can handle here. Maximum storage capacity achieving, you also want that. So initial work was 1 gram of DNA, they have showed about petabyte of information. But we know that theoretically the limit is 455 exabytes of information in the order of place for 18. So can we achieve that capacity, in a efficient encoding scheme? And of course, another problem is designing the chunk architecture of the DNA blocks. As I mentioned, the chunk architecture is important. Header, how much bits are in header, how many things, all those things are also very, very important. Okay. So So this is the first paper of church. So I'm giving you model what they have done. They took data source, they applied run length encoding, okay, sort of very standard technique in coding theory. Then they converted into, they applied DNA encoding. So basically converting those byte strings into the ACGT, then synthesis, sequencing and decoding. The chunk architecture was like this. There were few index bits. Length of the chunk was 115, okay, and certain bits were reserved for the index bit for each chunk. And I mean, you know, number of chunks was 54,899 and there was no error correction. This is a paper which you can, so I would suggest that please do read this paper, the first one, to get an idea how things were done, okay. Chunk architecture was bits, information bits, okay, and number of chunks. Okay. Main drawback of this paper was there was no error correction. Actually, when they did the experiment, okay, some music file or something they did, but so there were some errors. They corrected those errors manually actually. Okay, so it is kind of too much work. But that was the initial work in the first paper. Somebody is demonstrating that you can do that for larger files. Okay, and that was a celebrated paper in science. Okay. So, for example, in this scheme, if you take DICT, ASCII values are this, binary values are this, right? The corresponding binary values. Then ACGT. I mean, they still call it bit from a computer science perspective, but actually it's ACGT. So they call it nucleotide. So now, so basically here the chunk architecture was, so after converting it to binary values, 19-bit barcode appended for DNA block identification. So barcode suppose is this is appended here. That was information block. This is barcode. Then here the mapping was very simple mapping. 0 is converted to either A or C, 1 is converted to either T or G. And you can see that there are repetitions. For example, CC is here, right? CC is here, repetitions are there, right? Okay. So it's not very efficient one, but it worked actually. They did all manually. This was the very first attempt, you know, when they tried to do it. Okay. This is how, but indexing was important. Otherwise, how will you identify chunks? Okay. Then primer sequences were added, you know. So you call it 22 ACGT bits, basically. 22 nucleotides are added at the beginning and towards the end. Those green ones are added as a primer sequences. Primers word is used in biology for short strands of DNA. Okay, and that's very, very common thing. So this is the final DNA. Okay, for DICT. Now, Goldman model, so remember there the length of chunk was 115. Here they also added parity bits on the information bits, index bit, and parity bit. Parity bit, you know, like checksum, right? So everything is, you know, so you compute this. Okay. Here the length of the chunk was 117, number of chunks were this much, and they use 4-fold redundancy for error correction. This is something very unique. They have the error correction capability. I'll show you how. Okay. And here, rather in place of run length encoding, they use half-pen coding. You know, half-pen is used for data compression, right? You might have done it something in discrete mathematics also, you know. But here they use ternary, not the binary half-pen, ternary encoding. And all the other blocks are similar. So this is also an important paper for you to read from 2013. I mean, unfortunately, because there is no book, you need to look at these papers only. So here's an example. Take DICT. These are the ASCII values. Now this time, so this is the ternary half-pen codes basically, okay. ASCII values are converted into ternary Huffman codes. And so length is encoded in ternary. Okay. So something like this, you see S2, S3, and S4 are formed. Basically, more blocks of zeros are added here. So the chunks are required of certain length, right? So you had pad with zeros, and then those kind of things are done basically. So last one is the total length. This last string is encodes the length. So here is the final output. Then the Goldman scheme. First time they use this map, which is very beautiful map. We have worked on this further and we modified it. So what it does, so this map converts binary ternary strings into ACGT string such that no two ACGT bits are repeated. AA will not come, CC will not come, GG will not come, TTT will not come. So what you assume anything previously written, suppose nucleotide is A. So starting from 1, so basically 1 is converted into G. You see G is here. Assuming that the previous nucleotide written is A. You can start with anything, that's not a problem. I'm saying that suppose here initially before C it was A. So then I'm using 1 will give you G. Then go to the next one, which is again 1. Okay. So this time previous bit is G here. Right? So 1 with G will give you A here. So we have A. Right? Next is 0 there. Now 0 with A. 0 with A will give you C. So we arrive at C. Right? Any question? You know how it is moving? Yeah, you can assume it is C, G, T, and it doesn't matter. The mapping will work. So what I'm saying that when you want to convert the first bit, you have to assume that previously some nucleotide is there to use this table. You can use anything. It doesn't matter. Yeah, that, all that. Once you fix it, then you know what is going on, right? So for all things is converted into ACGT. Beautiful about property about this is that no AACCGGTT is repeated. Although there some zeros are repeated, but you see here zeros are not repeated. That is the beauty of this map. So we actually, from ternary to ACGT, this map is there. We found many such maps. Not only that, we tried to extend. Can we do the similar map directly from binary to ACGT, having this property? That's a beautiful, interesting thing to do. Binary to ACGT with no repetition. So we have done that also. Can we extend to ternary to more than ternary? So suppose we go to quaternary or say Curie symbols. If there are Q symbols, can we have these kind of map? It should do our job. Right? That's an interesting mathematical question we asked. So I think one of my students, I mean, the way it is constructed, he saying that for more than 3, it's not very. Obviously, you can modify and plenty of things are open to you. The question is, take the, because if we can apply directly on bits, we can have direct connection, right? Here we have to go into the ternary and then the convert. Any question at this map? Clear? So now you can see that there are chunks like this of here length 100. Chunk 1, chunk 2, chunk 3, right? Created. Then we put these chunk identifier, So I1, I2 be intra-file location of 12 bits for chunk 1 and chunk 2 respectively. So I1 is this, I2 is this, just some chunk order. So identifier of the file, ID1 is this, and that is the file identifier. And then parity bit, sum of all positions in chain index 1 and ID. Here P1 is 0 plus 0 and P2 is also 0 plus 0. Chunk index 1 is something like this, id.i.p and this. So overall, again that is converted into ACGT. Chunk index for 2 is again converted into ACGT. All these engineering things, right? How the header is, designed. And so finally, we have 2 of these chunks. Okay. They are converted like this. Okay. Now, in the Goldman encoding model, the repetition, how the 4-fold redundancy is introduced, binary file is there, base 3 encoding is done, ternary strings are generated from binary. I have not told you how it is done here, but once you get that, you convert into ACGT using this map, which is known as polymer map, and then you have these fragments. The indexing is done. So 4-fold redundancy added by repeated reverse complement of DNA each alternate fragment. Okay. So just to locate, this is something really interesting. So we implemented, I think Charlene implemented this paper of Goldman. We implemented it and we realized that there is a problem. 150, more than 500 MB, there was a problem in encoding. Okay. More than 500 MB file, there was an issue because of the chunk architecture was fixed. So we modified. We said that can we avoid 4-fold redundancy and we still keep the chunk architecture almost similar, okay, and correct the errors. We use very clever technique, again from coding theory. I'll show you how that we can still correct the errors at the same level. Okay. So it's a bit complicated actually for you maybe to understand. It's just, repeated reverse complement of DNA in each alternate fragment. Like that, it is added. Okay. One can work out a more detailed example. Yeah. Okay. So, and this is the DNA indexing information to locate the DNA fragment. It's a bit lengthy, but anyway. So now, once we modify, this was the paper in FNano 2014, what we presented here. Then we modified with another technique. So initially we modified the algorithm, which was published. Later on, we found a totally new way of correcting the errors. Vijay, Madhav went to LinkedIn, I guess, and Vijay is in ISKCON. He has become sadhu after this work. Okay, so he got offer of PhD from Iowa State University, but he left that. Fully funded, right? So that is it. You can meet Vijay. He's here only. Very good person. Anyway, so I think here I will explain this technique actually how it works. Or maybe next time because I need to. I'll talk about these 2 models actually. Both of this is our work in the initial days. Now we are doing something else, but I'll tell you how the Gole subcode encoding works and so on and so forth. What is Gole code? Gole code is also perfect code. If you draw the spheres, they cover the whole space. So I told you repetition code 0, 0, 0, 1, 1, 1, that one, all up to odd length. Then Hamming code and Gole code. These are the only 3 codes which are perfect code. Okay, so we have used Gole code here actually, one of them. Okay, so I show you that thing. And then we studied certain bounds actually in this in the other paper. We'll talk about this in the next class. Okay, and then from there we go further in different other codecs actually. After that, what has happened? After our work, what has happened? Okay.